And good morning, good afternoon, good evening, wherever you are. Hopefully you can see me because I can't see a camera at the moment. Sam, are we live at the moment? So Sam, I think we're live, but I can't hear you, and I believe people can hear me. I can't see myself either, which is unusual. Can everyone hear me? Can you just type in the chat box if you can hear me? Yeah. Okay. Good. Well, you don't need to see me. That's fun. That's the good news because I'm not presenting. So I'll just go on as if you can hear me. Welcome to the 101 nanoindentation seminar that we've put together for today. This is a talk that will hopefully take us from the fundamentals of the technique through to the giving some idea of the possibilities of the technique. Hopefully in the first of a small series that we'll put together covering different aspects of nanomechanical measurements. We've got 3 speakers today. Each talk will last about 40 minutes, so there'll be 2 hours in total. First speaker will be Andy Bird from Micromaterials, who will give us an introduction to the technique. After that, Professor Ben Beek will talk about indenting in extreme environments. And at the end, Adrian will talk about nanotribology applications. Each section will be 40 minutes long, so it'll be about 30 minutes, and there will be plenty of opportunity to ask questions. In fact, what I would encourage you to do is to write your question in the chat box as we go along, and then we can pick it up at the end of the talk, at the end of the 40-minute session, and we can have 10 minutes at each session to run through them. And in addition, we can pick up questions at the end as well. So if you have a question, please put it in the chat box. That way, Sam, who's organising this talk, can capture it and queue it up for answering at the end of the sessions. At the end of the session, you will see that we'll be able to log on to get a certificate of attendance if that's something that you would like to say that you attended the presentation. There will be a web link for that. Also a web link to future talks. And during the course of the talks, occasionally you'll see a poll question pop up, polling just to find out who you are, what you can do, what you want, what you're interested in. And there'll be an opportunity to download some technical handouts as well during the course of the talks. Those will pop up in the box that typically on the right-hand side of your screen. I hope that's relatively clear. Certainly clear in the picture you're seeing of me. I will, at that point, hand us over to our first speaker, who's Andy Bird from Micromaterials, who will talk about the fundamentals of the technique, try and give us an introduction to the principles. Andy, are you ready? I can see that you are.
Hi, Krish.
And I can see you as well, which is good because you don't need to see me, but it's much better to see you. Yeah. Okay, so I will cut my camera at this point and cut my microphone and hand over to you.
Okay, thank you very much, Krish. So welcome everybody to this Nanoindentation 101 seminar. So first of all, I'll talk about indentation, so an introduction to nanoindentation. So let's get straight into it. So first of all, a quick introduction to the company. So Micromaterials provide innovative and versatile nanomechanical test instrumentation. And we were established in 1988 by Dr. Jim Smith. We are specialists in nanomechanical testing. Originally, the system was a simple nano indenter, but we've been able to adapt the unique loading head to include many other different types of test, such as nano scratch testing and nano impact, which we'll hear more about in the talks later on. So we have a global user base. Most of our customers are universities, and we also collaborate with many of our customers, many universities. In fact, some of those collaborations have led to many of our capabilities and test techniques that we can do. So we're based in Wrexham in North Wales. So as you can see here, so if you're ever in the area, then feel free to pop by. Okay, so let's get straight into it. So first of all, an introduction into this presentation. So we'll start off by looking at hardness testing, a sort of brief history of hardness testing. Then we'll move into nanoindentation theory. Then we'll look at all of the different factors that can affect nanoindentation data. And finally, I'll just highlight some of the common applications of nanoindentation. So first of all, a brief history of hardness testing. So first of all, hardness itself, we have to think of it as a characteristic of a material rather than an intrinsic fundamental property of the material, such as elastic modulus. Okay, so generally it's defined as resistance to indentation. Okay, so resistance to plastic deformation when we apply a load through an indenter onto the test specimen. So the first standardized and widely accepted indentation hardness tester was the Brinell hardness test, which was invented by this man here, J.A. Brinell, a Swedish engineer at the turn of the 20th century. So, hardness testing goes back, in terms of sort of standardized techniques, goes back, well over 100 years. Then shortly after that, in the early 1920s, the Vickers hardness test was developed, which is probably the most common type of macro scale hardness test, which I'm sure you're probably all familiar with. So this was invented by these two British engineers at the company was called Vickers Limited, which is a large British engineering company in the 19th and early 20th century. So they developed this Vickers hardness test. And then around about the same time, the Rockwell hardness test was developed in the United States by these two gentlemen here, Stanley and Hugh Rockwell, who apparently were not related, coincidentally. But this test was also developed around about the sort of early 1920s. So let's look in a bit more detail at some of these test techniques, and then we can compare them to the modern day nano indentation. So with Vickers indentation, as I'm sure you're probably all familiar with this, step one is we apply a force through a Vickers indenter, okay, which you can see in the picture here. This is a four-sided pyramidal indenter. So the force is applied through the indenter into a test specimen, and of course we get an indentation into the sample. So the indenter is pushed into the sample with a known load. So usually, as you can see here, between 1 and 100 kilogram force. Okay, so in terms of newtons, that's times by 9.8, then we get the equivalent force in newtons. So it's roughly 10 to 1,000 newtons. Okay. And then step two is to measure the indent. Okay, so after the indent has taken place, we use the optical microscope to essentially measure the diagonals of the indentation. So the two diagonals, and then the average is determined. And from that, we can get the surface area of the indentation. And quite simply, the Vickers hardness value is the force divided by the area. Okay, and that gives us a HV value. So this technique, as we've seen, has been going for well over a century, and is commonly found in pretty much all material science and engineering departments. And similarly with Rockwell indentation, so slightly different here. This starts off by applying a minor load. Okay, so as you can see on this table on the right here, we have various different scales for the Rockwell hardness test, and it tells you the minor load, which is 10 kilogram force, and the major load, which, as you can see, is variable dependent on the scale. So what we do here is we're measuring the difference in depth of the indenter between these two loads, minor and major. Okay, and again, the different scales are for different types of material. It also depends on the thickness and the homogeneity of the material. You can see not only does the major load change, also the indenter changes as well, depending on the different scale. So you can see there's some diamond cones here, and the rest of them are steel balls from 1/16th to half an inch in diameter. Okay, so all of these might call traditional test techniques, such as Vickers, Brunel, Rockwell, they of course use very high loads. So between 10 and thousands of newtons. I think the Brunel test is usually 3,000 kilogram force, so 30 kilonewtons applied through a 10 millimeter diameter tungsten carbide ball. Okay, so these are very high loads, and therefore we cannot test very small volumes of material with, especially thin films and coatings, with these test techniques. They also do not provide a continuous record of load and depth during the indentation. Okay, so they're just essentially designed to make a big hole, a big indentation into the material, and therefore we don't get this record of depth as the indent progresses. Of course, they only provide a measure of hardness, so we can't really get any other information such as modulus or any time-dependent behavior. And these traditional techniques are not particularly adaptable for other types of small-scale mechanical tests, which I'll describe a bit later on. Okay, so why do we use nanoindentation? Well, the technique was developed in the 1980s to test thin films and coatings. Okay, so there was an increasing need to be able to characterize the mechanical properties of these coatings, which may be microns thick or even hundreds of nanometers thick. So of course, as we've just described with the previous traditional test techniques, the high loads applied would go through, would immediately sort of penetrate through any thin film or coating. So we need an indenter with a much smaller load, more precise application of these small loads. So when we're testing coatings in nanoindentation, there's a very general rule, which you may have heard of. It's called the 10% rule, which means in order to avoid influence from the substrate, the indentation depth should be no more than 10% of the coating thickness. Okay, so if we have a 1 micron thick coating, then the indentation depth should be no more than 100 nanometers. Okay, so obviously that small depth of indentation is not possible with the more traditional test techniques. So that rule works quite well for hardness. It's less applicable to modulus for reasons which we'll discuss later on. So nanoindenters, of course, they developed to test coatings, but they can be used to assess the mechanical properties of all types of material. Again, we'll look at that in more detail later. And the second key reason is that we can use the nanoindenter to target indentations into very precise locations. Okay, and that means we can characterize mechanical properties of individual phases within a material. Okay, rather than doing just one big indentation. So the example shown here is a high performance concrete sample, So you can see there are different phases within this material, the fiber, sand, paste. So with the nanoindenter, most nanoindenters come with an optical microscope, and we can use that along with the precise movement of the sample stages to position indentations within these different phases. Okay, so we can assess the what we call the local properties of these phases, as well as the overall response of the material. So different indenter types for nanoindentation. So the Vickers indenter, which we saw before, is the four-sided pyramid. The Berkovich indenter is most commonly used for nanoindentation, which we'll discuss more in the next slide. The Knoop indenter is not that often used really for nanoindentation, but conical or Rockwell type probes and spherical probes, they can be used for nanoindentation and also other types of testing such as nanoscratch testing. So the Berkovich indenter, as I say, this is most commonly used for indentation, nanoindentation. And it was designed from the outset to have the same ratio of contact area to indentation depth as a Vickers indenter. So the geometry of the indenter, the face angles, it was designed from the outset to have this equal ratio with the Vickers indenter. Incidentally, it was named after the Russian scientist that devised the geometry, who's obviously called Berkovich. So the reason it was a three-sided rather than a four-sided pyramid is because it's simply easier to grind the diamond to a fine point with three sides compared to four sides. Okay, so if you have a four-sided pyramid, it's hard to get this precise tip of the indenter, very sharp, which is of course very important for nanoindentation testing because some of the indentation depths are very, very small. So the precise geometry of the tip is very important in order to get accurate mechanical property measurements. So of course, it's not infinitely sharp, it's not perfectly, the very tip of the indenter. So what we usually see is the tip of the indenter is effectively like a sphere, a small sphere of radius, typically between 20 and 100 nanometers. So if it's a brand new indenter, it may be around 20 to 40 nanometers. And then, of course, over time, that tip will start to round and the effective radius will increase. Okay, so overview of a nanoindentation. So this is a typical nanoindentation curve, or what we call hysteresis in the graph here. So we plot the load on the y-axis, usually in millinewtons, and we plot to the depth or the displacements in nanometers on the x-axis. Okay, so we can see this is a sort of typical indentation that we might get from it looks to me like a fused silica indentation, which we use as a reference material. So essentially, the system, or most nanoindenters have some sort of surface find procedure where they detect the surface or the zero depth point of the sample, and then the load is increased to a target value at a rate or a displacement rate or a loading rate determined by the user. Okay, so in this particular example, it's loaded up to 50 millinewtons. Okay, and then after this is what we call the loading curve, and then usually after a short dwell period where we hold the maximum load constant, we have the unloading curve here. So this is where the load is reduced. Okay, and again, the user can define the loading rate, or rather the unloading rate here, until we get down to zero load. Okay, so of course the load and the depth data are plotted in real time. And we can run many indentations on one sample or several samples. We can run it automatically, so we can get a lot of data relatively quickly. So in terms of the analysis, how do we get things like hardness and also elastic modulus from this fairly simple plot? Well, first of all, in terms of these equations, load is denoted as P, capital P, and the depth is H. Okay. So this is the most common model that is used for the analysis of nanoindentation data is called the Oliver and Farr method. And this is what is described here very briefly, of course. So first of all, the power law fit is made to the unloading curve, okay? And this is used to determine the contact stiffness. So this term here. Also determined from this is the contact depth, which is HC, okay? So you can see on this, for this particular indent, HC will be around about here. So you can see it's basically in between the maximum depth, which is almost 1.3 microns, and the residual depth, or the plastic depth, which is about 600 nanometers. So again, the determination of the contact depth is depends on the model used, but in terms of the Oliver and Farr method, it's the maximum depth subtracted by another term, which is the load divided by the stiffness multiplied by a constant, which is called epsilon. And for this is dependent on the geometry of the indenter. So for a Berkovich indenter, the epsilon constant is 0.75. Okay, so once we've got HC, we can then get the contact area. So this is what we're after really, the contact area AC. And for an ideal or a theoretically perfect Berkovich indenter, the contact area is equal to this term here. So 24.5 multiplied by the contact depth squared. So from that, we can then plug that into our equations down here. So the hardness, or the indentation hardness, is defined as the maximum load divided by the contact area. Okay, and what's called the reduced modulus is equal to this term here, which is the stiffness multiplied by this factor, which includes the contact area. Okay. So you can see the hardness, the equation is very similar to that of their Vickers hardness, where it's the load divided by the area. But for the Vickers hardness, it's the residual area. Okay, so the area is measured after the indentation, and it's measured optically, of course. Whereas for indentation hardness, we are the hardness is defined under load. Okay, so it's looking at the contact area, which is defined under the loading conditions. Okay, so we're not using the imprint of the residual indentation. Okay, so so the equation we've just seen here gives us the reduced modulus directly from the analysis of this indentation curve. So the reduced modulus represents the combined elastic deformation from the tip and the sample. Okay, so we can fairly easily convert that to the Young's modulus, or the elastic modulus, with this equation here. So we've determined the reduced modulus from the indentation. What we're after here is ES, which is the elastic modulus of the sample. So all we need to know is this term here, which is relating to the indenter material. Okay, so in the majority of cases, the indenter material will be diamond. So we just need to know the elastic modulus of diamond and the Poisson's ratio of diamond, these are well known. So all we need to plug in really is the Poisson's ratio of the sample. Okay, so in some cases that may be known, in others it may need to be more of an estimate. But from this we can work out the elastic modulus from the reduced modulus, and the software that we provide, the nanotest software, has a function to convert that, or a calculator to convert that for you. In most cases, for low modulus materials, there won't be much difference between the reduced modulus and the elastic modulus. So what you can see here is a fused silica indentation. Again, we use this as a reference material. And you can see the reduced modulus is 69.4 gigapascals. And if we convert that to the Young's modulus, that would come out about 72. Okay, so as the reduced modulus, or as the stiffness of the material decreases, then there's very little difference because of the difference in stiffness between the material and the diamond. But for high modulus materials, this it diverges. We have to make sure that we are quoting the the correct modulus. Okay, so of course different materials will respond in different ways, and the shape of the indentation will depend on a variety of mechanical properties such as the hardness, yield stress, modulus, viscoelastic properties. So we've got some examples on the in this picture on the right. So if you imagine a perfectly elastic material, where there's no plastic deformation, the unloading curve will essentially follow the loading curve back down. Okay, so it will be purely elastic. There's no permanent deformation there. And then on the other end of the scale, we have maybe like some polymers or soft metals in particular. We can have almost entirely plastic deformation, where the unloading curve almost comes down vertically because there's very little elastic recovery. Normally we'd have a hold period at maximum load, so we get like a step at the top of these indentation curves, especially for polymers. We can also, with a nano indenter, we can detect these small changes in the structure of certain materials. So for example, if we perform a nano indentation into silicon, then we often see these small steps in the curve, which are pressure induced phase changes. These can be just, on the order of 5 or 10 nanometers in magnitude. Okay, so it really does require a very precise and sensitive nano indenter to detect these features. And similarly for sapphire, we get what's called these pop-in events during the loading. Okay, so nano indentation, from this fairly simple load versus depth curve, we can obtain a lot of information, as we've seen, hardness and modulus, but also things like creep behavior, strain rate sensitivity, fracture toughness, yield stress, and more. We can also obtain plastic and elastic work from the indentation. So the area underneath the unloading curve represents the elastic work done by the indenter, and the area enclosed by the loading and the unloading curve is the plastic work. So there's a few sort of indexes, such as plasticity index, which is the plastic work divided by the total work, and also the hardness to modulus ratio, so simply the hardness divided by the modulus. We can use these indexes or parameters as a useful prediction in terms of tribological behavior from indentation data. So my colleague Adrian might talk more about that later on. Okay, so factors that affect nano indentation data. As you can see, they are numerous, and I've split them up here. I mean, this is just more common ones, of course, but I've split them up into 4 general categories. So first of all, we have the environment. Vibration, mechanical vibration or acoustic vibration can affect nano indentation data, as can thermal drift, which is thermal stability of the instrument. In terms of the instrument itself, frame stiffness or compliance, it's sometimes called, and indenter geometry. These are important factors to ensure that we get accurate and reliable mechanical data. Sample preparation, so sample mounting, surface roughness, these can affect the data quite a lot. And also properties of the sample itself, so things like indentation size effects, pile up and sink in, and residual stresses. So we'll look at these in a bit more detail. So first of all, we go back to the environmental considerations. The thermal drift is essentially a change in the dimensions of the instrument due to a thermal expansion or contraction of the instrument itself. Okay, so if the nano indenter is situated in a location where there isn't really any temperature control, then we will often see what's called thermal drift on our measurements, which is essentially a change in depth imposed on the indentation data due to this contraction or expansion. So basically, it's an error which we need to try to eliminate or minimize as best we can. So generally speaking, most nano indenters housed within some sort of chamber or cabinet. So you can see here, this is the Nanotest Vantage, which is the nano indenter that we make here at Micromaterials. And you can see it's sort of housed in this this cabinet. So these cabinets can be temperature controlled. For the Nanotest system, if the lab itself is kept temperature is kept constant, within 1 or 2 degrees Celsius, then normally we have very, very low rates of thermal drift, and so we don't need to worry too much about it. So the other environmental factor is vibration. Okay, because the key thing with vibration and also thermal drift is with nanoindentation, we're measuring on a nanometer scale. Okay, we can be doing indentations that have a maximum depth of less than 100 nanometers or even less than, say, 20 or 30 nanometers. So any vibration through the ground or even through the air, this can introduce noise, sort of very sort of spiky looking indentation curves, which can affect the well, it can affect the hardness and modulus values that you measure. So again, most systems will come with some sort of anti-vibration platform. So then the Nanotest system uses what's called a -K system. That's the brand name of the platform. And this is a passive system, which is very effective at eliminating or significantly reducing the effects of vibration that get transmitted from the floor onto the system. Oops. Okay, so frame stiffness is another important factor. This is the contribution of the system of the loading frame to the measured depth. So you can see here, if we were to plot this contribution of the instruments, this frame compliance or this frame stiffness on the same plot as the indentation curves, we'd see essentially a sort of a linear straight line here. So during the analysis, the frame compliance is removed from the raw data. Okay, so you can see here, this is the indentation curve before the compliance is removed, and then this is what you might call the true sample response after this has been removed. So this is very important that the frame stiffness value is accurately determined, because especially for high modulus materials, such as, for example, tungsten, because if there's any inaccuracy, then it will significantly affect the reliability of the modulus values. So for nanotest systems, as it states here, the displacement is directly proportional to the load. Okay, so that's why we get this straight line, which means we can use a single value for the frame stiffness across the whole load range. Okay, so we can do an experiment whereby we perform a range of different loads on the tungsten, and when we analyze the data, we get the correct modulus values across the load range. So tip geometry, which we briefly mentioned before, once we get down to the very tip of the Berkovich indenter, then it's often more like a sphere with as we said, a radius of around 50 to 100 nanometers. So it's important that when we analyze indentation data, we have to include what's called an area function. Okay, so this essentially characterizes the geometry of the tip and relates the contact depth to the contact area. So this is particularly important if we're performing indentations that are very, very shallow, where the tip of the volume of the indentation is predominantly this sort of spherical tip area at the tip. Because if we don't include an area function, then we can get a significant overestimate of the hardness and modulus values when we're performing these very shallow indentations. So moving on to sample preparation. So surface roughness is a common source of worry. Generally speaking, the lower the roughness, the better. Okay, so when we indent a material with a relatively high surface roughness, then we tend to see more scatter or more sort of variable indentation curves, and of course larger standard deviations, or bigger averages in hardness and modulus. So if this is the case, then generally speaking, in practice, we would take more measurements to get a better statistical average. Of course, polishing the samples is preferable as well, if possible, because occasionally, the act of polishing it may change the mechanical properties itself, so it's not always desirable to do that. It's also worth mentioning that the samples should be securely attached to the sample holder. So you can see a few examples of some samples here. If the sample is not properly attached, then this will give us erroneous results. So typically low hardness and modulus values if it's not properly attached, so that when you're performing an indentation, you're actually pushing the whole sample back if it's not been adhered to the sample holder properly. And of course, the samples must be clean. So any dirt or grease on the sample, for example, if you touch it with your finger, then that will likely affect the indentation curve and therefore the analysis results. Okay, so there's a few other sample properties which can affect indentation data. So first of all, there's these two things called pile up and sink in. This is, you can see from the diagram on the right here, pile up is where the sample material essentially piles up around the indenter during the indentation. Okay, and conversely, sink in is where the material is pulled in away from the, or dragged down towards the indenter. So you can see how this affects the contact depth, HC. You can see on the diagram here, you can see that in the case of the pile-up, it's maybe slightly exaggerated, but in the case of the pile-up, HC is actually larger than the H, or the maximum depth. And for sink-in, it's a lot smaller than it would otherwise be. So the standard Oliver and Farr analysis that I briefly described earlier does not account for these effects. So there are other methods in which to account for these features. And also indentation size effect. So in some materials, we often see an increase in hardness near the surface, okay, which is not due to any sort of errors in indenter geometry or calibration. So this can be due to a number of factors, such as the presence of residual stresses, strain hardening, as I mentioned previously, from polishing perhaps, or the presence of a very thin oxide film on the sample surface, or even friction between the indenter and the sample. Okay. So as you can see, there are a lot of factors that we need to consider when performing nanoindentation data. Okay, so to finish off, I'll just quickly go through some common applications of nanoindentation. So as I said at the beginning, most nanoindenters can be used to test pretty much all types of material. So in terms of the nanotest system that we have two loading heads. The low load head, which goes from around 0.01 millinewtons to 10 micronewtons up to 500 millinewtons. So this gives us a very wide load range and the ability to test all different types of material. So from very soft, very low stiffness biological samples, all the way up to hard wear-resistant coatings. So a few examples here, just go through them very quickly. This is indentation data from the nanotest in the basically measuring material stiffness in the kilopascal range. Okay, so this is work done by MIT. So we have these very, very soft, low stiffness materials, biological materials, also hydrogels, which have stiffnesses on the order of kilopascals. And similarly here, this is a indentation on a hydrogel, which you can see here, the indent has been performed in a liquid environment, in the wet environment, and this has a modulus of 3 megapascals. So we're able to test very soft, very low stiffness materials with the nanotest and most nanoindenters, in fact. But we can also test very, very high stiffness materials. So this is an example, again, from one of our nanotest systems of indentations on two synthetic diamond coatings. Okay, so we can see the hardness down here around 90 gigapascals, the reduced modulus around 600, and that equates to a elastic modulus of 1,000, over 1,000 gigapascals. Okay, so in order to measure, accurately measure materials of this hardness and high stiffness, then it's important that we have a stable and precisely calibrated instrument. So as I mentioned briefly in the section on frame stiffness, any slight error or inaccuracy in the frame stiffness determination will give us large errors in the modulus values. Of course, when we're indenting materials as hard as this, we need to watch out for indenter wear, okay, because it's a bit of especially samples like this, very hard and also quite rough as well, these synthetic diamond coatings. It can be a bit of an indenter graveyard. So another common application of nanoindentation is to measure mechanical properties as a function of depth. So this is particularly useful for coated samples, thin films and coatings. So there are different ways we can do this. Often it's done with a load oscillation technique, but it can be done with a standard quasi-static technique, such as the one you can see here. This is what we call a multiple load cycle test, whereby we perform an indentation with these increasing load steps. So the load increases, and then we have a partial unload period, and then the load then increases onto the next step. So this is a single indent in one position on the sample, but with these multiple unload steps. And we can use the standard Oliver and Farr analysis to get a value for hardness or modulus for each of these unloading steps, and then we can plot that as a function of depth into the sample. So in the example you can see here, this is a 2 micron thick titanium nitride coating on a silicon substrate. And we can see that this is the hardness here. Okay, so we have a peak hardness of around 18 gigapascals in this region here. And you can see as the load increases, as the depth increases, we get an increasing influence from the silicon substrate, and the hardness then decreases and essentially just tends towards the hardness of the silicon itself. So we can see these three regions here. So the first region is where the hardness is actually slightly lower. This can be due to surface roughness. It can also be due to a non-fully developed plastic zone if the indent depth is very, very small. And then we see it increase and sort of plateau. So we generally regard this plateaued region here, number 2, as the true coating hardness in this case. And then, of course, region 3 is the area of increasing substrate influence. Mechanical property mapping is another common application. So this is where we perform a large number of indents very quickly over a given area of the sample. The area is typically tens of microns. So in this particular example here, we've used the nanotest to perform an indent grid containing around 2,000 indents on a sedimentary shale sample. So we can see, once we've analyzed the data, we can take the hardness and modulus values and plot them into this sort of 2D or a 3D color map. So we can visualize the variation in hardness or modulus over this area. So you can see I think the area for this particular experiment was 45 microns, 45 microns square. And we can see how the modulus, I think this is the reduced modulus, changes over the sample. So we can see these low stiffness regions, these sort of, I guess these are the clay matrix, these sort of pink and purple regions. And then we have these regions of much higher elastic modulus, so 150 gigapascals. Okay, so that's a useful way of visualizing the variation in mechanical properties graphically. Okay, so creep and viscoelasticity. So we can use nanoindenters to investigate time-dependent behavior, which is something obviously we can't really do with the traditional test techniques. So dynamic nanoindentation has been used for this purpose for a long time. So this is where we have a load oscillation imposed over the normal load. And from this, we can determine things like the loss and storage modulus and tan delta from the data. And we can also obtain these things from quasi-static indentation. So we can use perform a nanoindentation and with a long hold period, or what we sometimes call creep testing. And this can be used to extract properties such as creep strain rate sensitivity and creep compliance for these time-dependent materials. So the thermal stability of the test instrument is important. So I described earlier on about thermal drift and how we minimize that. This is particularly important for these types of tests where the indenter is in contact with the sample for a long period of time. Okay, so I mean, in the example here, this is a creep curve on a polymer material. So this is 800 seconds. Okay, so this is quite a long time, and we can perform creep tests that are even longer than that. So it's important that, especially for these types of tests, that we have a system and an environment that is thermally stable. Okay, so that brings me to the end of my part of the seminar. So just in summary, what we've looked at today is the difference between essentially nanoindentation and some of the more traditional techniques, macro scale hardness tests such as Vickers and Rockwell, and how we can get a great deal more information from the nanoindentation than we can from traditional indentation. So nanoindenters are designed to study mechanical properties of all different types of materials. So we've had a quick look at examples from very low stiffness materials right up to very, very hard diamond coatings. And also nanoindentation has been used for, as we've seen, a wide variety of applications. I mean, we've only looked at a very small number of some of the more common applications, such as depth profiling and mechanical property mapping. But nanoindenters can also be used to perform more novel techniques, such as things like micro pillar compression or micro cantilever bending, which again use the fact that we can have this precise positioning of the system as well as the precise load application and displacement measurement. Okay, so thank you very much for listening to this first section. I'd like to ask if there's any questions for me this time.
Okay. My camera's working now, so you can see where I am.
Oh yeah, very good.
I don't know why that was, but anyway, yeah. So we take 5 minutes of questions now because we're pushing time a bit.
Yeah, sure.
And then we'll follow up at the end in more detail, and just keep going till we get through all the questions left. So the first question has come on the screen now for you, Andy, from Gabor. If the material is anisotropic, how can reduced modulus be obtained?
Well, reduced modulus is, we're just measuring the modulus at the point of the indent. Okay, so of course the modulus, the reduced modulus of the material may change. If it's a anisotropic material, multi-phase material, there can be variations in reduced modulus and therefore elastic modulus. So the only consideration is when we're converting between reduced modulus and elastic modulus. All we need to know essentially is the Poisson's ratio and the elastic modulus of the indenter material, and also the sample as well. And again, it may be difficult to do that with some samples, especially if they are, say, multi-phase.
Okay, lovely. From Gabor again, how can you calculate the yield strength?
Yeah, that's probably one for Ben, I think, if he's available, or maybe Ben can answer that towards the end. But it's something we can obtain from indentation. I think it's often done by using spherical indentation.
Okay,
But
so we'll save that question till later then.
That probably
we can mark that as unanswered in some way and put it into Ben's questions.
Yeah.
Okay. How do you calculate the effect of pile-up or sink-in from the material properties, especially in viscoelastic materials such as polymers?
Often they can be. It's done by performing imaging the indentation after the experiment has been performed. So, with the nanotest in particular, we can image the indentation with the nano positioner, the piezo stage, or also we have a possibility of integrating an AFM onto the system. So generally, it requires some sort of imaging of the indentation to ascertain the pile-up or the sink-in, and then using that information to apply that to your nano indentation data.
Okay, very good. Let's take two more, and then we'll cut to Ben's talk, and we'll come back to all of these at the end then of the session. And if people are patient, we'll try and answer every question at that point. From Gabor, does the indenter need to be cleaned regularly? And if so, how?
Yes, that's definitely an important factor, because over time the indenter can pick up debris from various samples, and if the debris is covering the tip, then that can significantly affect the reliability of our data. Generally speaking, we would perform reference indents on the calibration sample, such as fused silica, relatively frequently, and that will tell us if we've got a problem with the tip. And if it does indicate that we've got a problem, then the first step would be to clean the indenter. And we do that simply by different ways. But it's typically like a cotton swab that's soaked in ethanol or alcohol, and just gently rubbing the tip of the indenter with the swab. And that usually will remove most debris from the indenter tip. Another thing you can do is just perform an indentation into a sort of soft metal, like copper or aluminium, to maximum load, and that can sort of push the debris from the tip up the indenters. That can help as well.
Okay. Well, I'll take one more then question, then we'll move on to the next talk. But as I say, we'll come back to these questions at the end of the full session. In practice, how do you attach different samples to the holder? Another question from Gabor.
Normally, we would. It depends if the samples are of different height. I mean, we can, for the nanotest system, we can accommodate samples of different thicknesses or different heights, even on the same sample holder. So we can. I mean, if they're all less than a few millimeters difference in terms of height, then we can attach multiple samples to the same holder. In most cases, we just use a simple super glue to attach the samples, but we can have other methods if super glue is not appropriate, or if you want to be able to remove the sample afterwards, without risking damaging it. So there are different methods of attaching the samples, but generally speaking, we just use super glue, and so we can attach different samples, multiple samples onto the same holder, assuming that the difference in height isn't too extreme.
Yeah, and you tend to use super glue rather than double-sided tape for most samples because of the compliance.
Yeah, the double-sided tape, it's probably not a good idea, because you've got like quite a thick layer underneath the sample, which can act as almost like a cushion. And you apply the load, you can press the sample against this sort of cushion, and that will give you you'll measure a much lower modulus than you should be.
Unless your sample is a cushion in itself, I guess, which case
unless it's
negligible.
If it's extremely soft, compliance. Then
that's that's generally the way for most systems, that you need a very non-compliant interface, but particularly anything that's high. Is that correct? Basically, regardless of
yes.
regardless of the system, just a general rule of thumb.
Yeah, that's right. Yes.
Yeah. Okay. Very good. Okay, let me stop there because we've overrun by a few minutes. So I'm going to switch over to Professor Ben Beek. He's worked with micromaterials since, 2 years, I forget, but I'm sure he wants to forget. But no, plenty of time. I was also visiting professor at a couple of universities, which demonstrates how micromaterials works with universities around the world as collaboration and joint enterprise. So on that very briefest of introductions, I'll hand over to Ben and turn myself off again.
Thank you very much, Chris. I hope everybody can hear me. If not, please say. So in this section of the presentation, I'm going to be talking about how we can use nanomechanics to design improved materials for operating under extreme environments. So it really follows on from Andy's talk. So I'll start off by just recapping a couple of the key concepts in nanoindentation and show how we can use the technique to really target highly localized mechanical property information, and we can do that with a range of different nanomechanical test techniques. And then I'll move on to the body of the talk to really discuss the influence of the test environment on the mechanical properties that you measure. So this is really about extreme environments. So we're looking at the effects of humidity and liquid, so moisture effects. We're looking at the effects of strain rate on mechanical properties of materials. And we're also looking at the effects of temperature. And in this presentation, I'll be focusing on high temperature, but equally low temperature is also important. So this is a typical indentation curve, very similar to the one one of the ones Andy showed you, where we're loading up and then we're unloading, and we have some partial elastic recovery in the material. And the contact mechanics analysis, typically this power law fit to that unloading curve is done, and then that gives us the mechanical property information, specifically the hardness and the elastic modulus of the material in a standard test. And as Andy mentioned, the shape of the curve, the amount of elastic recovery is intrinsically linked to the mechanical properties of the material. So it's intrinsically linked to this ratio of hardness to modulus. And that's why typically you can think of the technique really as a mechanical fingerprint for a material or for an individual phase in a material. And we can design different tests, as Andy described, to look at time-dependent deformation. We can move to spherical indenters to look at stress-strain behavior. We can also look at yield stress as one of the questions just now. So with to get yield stress out of an indentation test, you have essentially a couple of different approaches. You can measure hardness, and then you can use the constraint factor to relate hardness to yield stress, so that's constraint factor is about 3 for metallic materials, but it's a lot less for ceramic materials, so that gives you a reasonable estimate of yield stress. Or you can switch to spherical indentation geometries, and these geometries allow you to be in a fully elastic regime initially, until as the load increases, at some point there's a move to plasticity in the material, and which you may see as the curve as a pop-in, as Andy showed the example on sapphire. And you can relate that mean pressure at which that pop-in occurs to the yield stress through the relationship of the mean pressure at yield equals 1.1 times the yield strength. So that's an easy way to do it as well. You can also move to very, very sharp tips, and then you can generate cracks, and you can measure the length of those cracks and generate fracture toughness measurements. So with subtly changing the type of test we do, we can generate a huge amount of different mechanical property information. So one area where it's, as the technique has become more established, getting increasing amount of different applications is in the aerospace sector. And there's lots of different industry drivers for that, of which perhaps the main two are to try and save weight, to reduce the fuel costs and the environmental impact of flying, reduce the amount of CO2 emissions, and also to develop more reliable materials in jet engines that allow us to go for longer between services, and again improved reliability. So there's a range of different applications showing materials that have been tested. Pretty much anything on the aeroplane has been tested by nanomechanical testing. So some examples from the aerospace sector and elsewhere are shown here. And here where we're talking a little bit about using grids of indentations, using the automated ability to position in a single setup. The instrumentation gets all these different does all the indentations in either specific targeted positions, or in this case in grids. And here we can see a few different examples. On the right we can see an intermetallic compound in an automotive aluminium alloy, and that's showing essentially that it's much stiffer than the surrounding aluminium matrix. In the middle at the top is a titanium 6-4, which is a very typical material in the aerospace and biomedical fields. And when you look at this at small scale, you can start to see that the complex microstructure in this material actually gives it different mechanical property phases. So here you're getting one region where it's lower hardness, and here it's getting higher hardness regions. And this is down to the differences in the crystallography of the individual regions you're testing. Solder joints are particularly important because the solder joints can be brittle, and this can lead to reliability problems. So this is a mechanical property map of lots of finely spaced indentations, and you can see that the region in the vicinity of this joint is much higher hardness. The red is the higher hardness, and actually you can see that it has led to reliability because it's actually cracked after testing. And you can look at machine components, and you can even combine mapping with this depth sensitive information, as Andy described it, a load partial load test. And we can do each of those tests in the individual locations, and that allows us to build up slices of information about the mechanical properties going into the material. So in this case, this was in a composite material, and you can see there's a buried stiff phase in there that you're not seeing really at the surface, but as you go deeper and deeper, you're seeing progressively this stiff phase. You're also seeing a pore in this case. So this is very useful for building people that are interested in building up mechanical property information. So as well as these grid indentation experiments, we can also target specific features of interest on our material. So we can, for example, accurately place to really a couple of nanometers precision. So in this example, this is from MIT, and this is actually nearly 19 years old now. So we've had this precision, and we've been a leader in this industry for a long time. You can see how we can target put these indentations right in the middle of these soft pattern lines on a silicon substrate for a MEMS application. On the right, again, from a sort of aerospace application, we can target and we can position indentations in the middle of carbon fibers. This one here is for the automotive industry, and this was as part of a study illustrating you can put big indentations to understand these big phases, and then combine that with much smaller grid indentations to look at the mechanical properties of these more smaller phases. And this one is a biomedical alloy, again, where you can position automatically and get different phases in the spinel. So Andy alluded right at the end of his talk and said, well, there's, as well as an indentation test, there's lots of other things that you can do to take advantage of the fact you have this very precise control on the load that you apply, the displacements that you measure, and the position accuracy at which you do the test. So some of these are shown here in examples from universities of Cambridge and Berkeley and Oxford. And what they've done here, for example, is that they've used a focused iron beam to mill out a pillar of a material of interest, and then they've squashed that pillar with a flat punch. And again, this is another way to get out yield stress information from the test. They've also machined out cantilevers in this work from Oxford on the right, and then we push on the end of those cantilevers with a Berkovich indenter, and then at some point you get some elastic property information, and then you may also get some yield you may get some plasticity, and you may also get some cracking near the root of the cantilever. So again, this is all useful information, allowing people to pull out phase-sensitive mechanical property information. And this is from a composite, and this is these fibers have been pushed from the other side of this material, and this is just a sort of false color image that they actually put in to try and win a prize for the prettiest image. But there was some serious science behind this as well. Okay, so as I mentioned, one of the key industry drivers in the aerospace sector is to really get down the weight of the aeroplane. So if you go back 50 or 60 years, then 707s typically were they were pretty much all metal. There was no composite materials in there at all. But as time has gone on, we're getting progressively more and more composites onto the airframe. And now really with this Airbus A350 wide body plane, then you're really getting up even over 50% of the composites in the material. So the challenge is in combining weight saving whilst retaining sufficient strength in the material and sufficient safety. So one of the things that controls the safety of carbon fiber composite materials is their structural integrity, essentially. And to achieve that, you really need very strong bonding between the fibers and the surrounding matrix. And we have tested this, or our customers have tested this, by using, again, instead of sharp indenters, in this case flat punch indenters, typically with a geometry or a flat end of around 5 or 10 microns. And they take specially thin samples, and they accurately use the nanotest to target in the middle of one of these fibers, and then they push it down. And as they push, at some point, as the friction is overcome and the strength of the bonding is overcome, the fiber is essentially pushed out into the material. And you can see, if you look at the back side, then you can see the fiber sitting up. So they can do this for different adhesion strategies for the fiber and pick the best bonding for the application. So this is an example, an SEM showing the consistent way that these fibers have been pushed out. This is the back side of the sample. And we also have the load displacement curve as we load up, and there's an abrupt yield here where the fiber slips, and then it recontacts again because let's go back. As you can see that it's a flat end, but there's some geometry to the indenter. So as you push down, you recontact further up. So both of these features you see very nicely in the data. We can also do these type of tests under more extreme environments. In this case, this is for another aerospace application. This is now silicon carbide fibers and a silicon carbide silicon matrix composite. And this is now at much, much higher temperatures. And also these loads are higher. So in this case, we use the high load head in the system. And we can see that these push-in forces are very temperature sensitive. So this again shows the importance of being able to test under the relevant environmental conditions. Okay, so moving on now to the influence of the test environment on the mechanical properties. I'll start off by showing this graph here, and I'll just say what is going on here. So that there's 4 indentation curves. They're all different colors, and they're all on the same material, and that material is very homogeneous. Very homogeneous. So it's mechanical. If you test at different positions, you get exactly the same results. So nevertheless, we're getting this big spread in behavior. So what is going on? What's actually happened is that the customer has changed the test environment between doing those different tests. So they've changed the humidity in the test environment. The relative humidity has been changed from 85%, which is this blue one here, then to 70 in this curve, then to 30, and then right down to the lowest humidity, very, very dry at 10% for the red curve. And they've done that with this little humidity chamber here, which my colleague Adrian designed. It works very, very nicely. Just sits in the nanotest system, and it allows us to very rapidly control that test environment. So rapidly change the humidity in the environment and then do tests rapidly. And in this case, as the test has been essentially gone from dry and then moisture's gone in, we can track how that material, in this case nylon, because it's sort of hygroscopic and it's very sensitive to the ingress of small water and organic molecules. Essentially, it's plasticized by that, and it gets less hard and less stiff. And you can see in the graph here how its stiffness decreases as a function of humidity, of increasing humidity. You can see how the users then move to look and actually developing a new improved material by putting a clay into that material, intercalating a clay, and that increases the stiffness of the material. But you can see that relative stiffness enhancement is not constant across that humidity range. So the enhancement in stiffness is much, much better in the composite material at high humidity. So this is very useful for applications where the nylon might be susceptible to these very moist environments, and it's suffering from not enough structural integrity. And it shows that there's a real benefit in putting making the composite with the 10% weight of clay in there. Okay, so moving on to the next subtopic is this. Now we're going to look at strain rate, and we look at that through nano impact testing. So in a nano impact test, essentially we can, in comparison to an indentation test, now it's a quasi-static test essentially. So it's in an impact test, essentially now we have a dynamic test. So instead of the load being applied very slowly, now we're applying that load very rapidly, and we can achieve strain rates of about 1,000 per second, which compares to an indentation and a normal quasi-static indentation where you would be typically about 10 to the -2 per second. So you're many orders of magnitude higher. And this allows you to look at high strain rate properties such as hardness, but it also allows you to look at to do the test repetitively. And that allows you to essentially look at fatigue aspects. So you can look at coating toughness and resistance to fatigue fracture. So you can go up, backwards and forwards, and you can think of it very much like this poor guy here. So essentially he's tapping away at that material until we get some material removal. So one application for this technology is in developing fracture resistant materials. So one application here is in optical coatings. And so these coatings have been designed obviously for their optical properties. And when you do that, sometimes their mechanical properties are less well considered. So in this application, the standard physically vapor deposited coating has been subjected to a nano impact test. And you can see here, very large impact crater, very brittle fracture, lots of radial cracking, and it's not a very well behaved material under these type of conditions. So in our customer here at the University of Oxford, they developed a new nanoparticulate coating, which was softer, but it was much less susceptible to this brittle fracture mode. So it shows that you can really use these type of technology to design better materials for these extreme environments. So, as I said, brittle systems are typically hard, so they use in a range of different applications, but they do have this intrinsic low toughness. And schematically, you can think about a high strain rate contact or an impact coming into a brittle material and causing a range of different deformation mechanisms, including some plasticity, but also a range of different cracking materials. And that's just on a single impact. So if you have multiple impacts, you can imagine these crack systems superimpose essentially, and then you get large amounts of material removal, and this leads to erosive wear. So The nano impact test has been used for a range of different applications. I'm just going to talk about a couple of them here. One is in optimizing or understanding how turbine blades in jet engines are affected by thermal aging. Another one about how we can use it to design coatings which have better life in high-speed metal cutting applications, because that's one of the big advantages. If you do have a coating that's more durable, then you can run it for longer and you can have improved productivity, you can run it faster. That's the real challenge. So in a jet engine, a thermal barrier coating is the key system that enables you to operate the jet engine above the melting temperature of the nickel-based superalloy, which is the turbine blade material. So it's quite unusual, if you haven't thought about it, essentially that by a combination of this thermal barrier system and advanced cooling, you can actually, every time you get in an aeroplane, I know we're not doing a lot at the moment, but every time you get in an aeroplane, to think that the temperatures in that engine are higher than the melting temperature of the alloys in the engine. And yet it's still working very nicely because of this very clever composite material, composite coating system that allows us to drop several hundred or 100 or so degrees across this zirconia top coat. So this one shows a more detailed example of one of these systems. But the downside is that in the engine, these thermal barrier coatings that protect the turbine blades are susceptible to a certain amount of particulate erosion, be it sand particles typically. That can be worse in dusty environments, but equally, even in any environments, there can be sand in the engine, gets ingested. And eventually it can lead even to dimensional changes in the blade, and it can be, under some cases, it can even be life limiting, essentially. So you can have an engine failure, and that obviously can have catastrophic consequences. So the manufacturers of these coatings really want to try and optimize their thermal properties with their erosion performance. And in a jet engine, obviously these things are susceptible to very high temperatures. They're in a very high temperature environment. So this is not a nano impact test result. This is an example from Rolls-Royce, where they're looking at individual erosion tests. They're looking at doing an erosion test and taking the coated part out and measuring it and putting it back in and continuing the erosion test. So it's a very time-consuming process. What you can see here is that this material here, this columnar thermal barrier coating, is being eroded away, essentially as a function of time here. But when you thermally age it, it's being eroded away more quickly, and particularly at this higher temperature of 1500 degrees. So the shorter exposure for the high temperature is even worse. So this is potentially problematic. It warns it influences how often these things need to be checked and serviced out. So we want to try and understand these things and design materials with better life. So we can simulate this erosion test, really quite simply by using the repetitive nano impact test. So we typically come up, hit at the same position on the surface. We can cause the cracks, and we can follow that deformation behavior. So here is an example of how it's working. So here we have 3 different impact test results. You can see the tests are really quick. They're only a matter of, in this case, 3 minutes. And we get exactly the same ranking of wear rate that we do in the much longer erosion tests. And if we look at the microstructure, we can actually see what's happening is that when the material has been thermally aged, this columnar structure, which provides some strain tolerance, is starting to sinter together. And that sintering across the columns is decreasing the strain tolerance such that when it's impacted or eroded, then essentially material from many columns can be removed. But when when it's not thermally aged, essentially that can remains within one column. So there's big disadvantages in this case for thermally aging. But this is just here to show the advantages of the nanotest and how to optimize this sort of performance. So say the other key application area for the impact test is in simulating metal cutting applications. So here's an example from the literature from one of our customers a few years ago. And what they've shown here is a very clear correlation between the number of cuts until the tool failed and the performance in the nano impact test. So essentially, when there's a very high depth at the end of the impact test, that's because the coating has fractured, and this is again correlating to a large degree of coating fracture in the actual test, which is leading to a very limited amount of tool life before it fails. And conversely, you can get a lot more life out of the material that doesn't fracture in the impact test. So if we now look and say, well, what is behind this trend? And what we can see here is how our customers here manage to optimize their coatings. In this case, is by tinkering with the microstructure. So they're putting extra layers in, and these extra layers are acting as stopping crack through thickness crack propagation. So the cracks are coming in, but then they're getting deflected perpendicular to the stresses, and this is minimizing the amount of wear that's occurring essentially. So it's localizing the fracture, and it's minimizing the amount of through thickness cracking. So another example here, again comparing two different cutting tools. So you can see on the left is the cutting tool test, and on the right is the impact test. And what we can see here is that this coating here, and this titanium aluminium nitride, starts off about the same as the other coating, but rapidly starts to fail more quickly. This one is this aluminium chromium nitride shows a much longer sort of fatigue period. But again, these cutting tests, you had to stop and test these things each time, put them back in the same position, start again. So it's a very time-consuming test. And again, if we look on the right, we can see the impact test, and we can see in a minute and a half we get exactly the same trend, very consistent behavior. This just shows one test, but you can do it several times and get very consistent behavior. And again, it shows this material is the best, and in this case again it wasn't the harder of the two materials, so it shows that you can't necessarily rely on mechanical properties alone to predict performance. It's much better to be able to simulate the test directly. So in the last part of my talk, I'm going to be talking about the influence of temperature, high temperature. So sticking with hard coatings now, so many applications of hard coatings and wear resistant coatings, when you think about it, really are high temperature applications, be they in metal cutting, be they in machining engine blocks, or be they in aerospace applications. So when we think about coating design for wear resistance, we typically think about wanting to combine hardness and toughness in materials, and particularly in coating systems. But what we really need to be thinking about is combining high temperature hardness and toughness. Excuse me. So how we achieve this ability to test at very high temperature accurately is done by having independent heating of both the sample and the indenter. And this dual heating, if you like, allows us to have a localized hot zone, and that localized hot zone allows us to do measurements without thermal drift. But otherwise, what you find and what our competitors find essentially is that they get large amounts of thermal drift that make the results unreliable. So you need to have this isothermal contact zone, which we've got in this patented hot stage shown here. So this has been used again by large amounts of customers around the world. And here's some work from Berkeley looking and showing how the hardness as a function of temperature decreases. Even in these quite hard materials, it decreases. And in this case, this alpha alumina stays harder than this kappa alumina throughout this temperature range that they've used in this case at Berkeley. Another example here showing 3 different titanium aluminium nitride based coating systems, and what we can see is that the curve in red, which typically looks almost as good as the others and better than this one at room temperature, actually has much worse thermal stability than the other coatings. And we can see really when the temperatures in the application due to friction are very high, really then you need this high temperature hardness and you need this high temperature yield strength of these guys, and this one is much worse. And this again correlated to the coating performance in these cutting in continuous turning tests. So when you want to go to higher temperatures, it's really a good idea to go to vacuum. This protects the indenter from oxidation wear, but it also allows you to protects the samples as well from oxidation. It allows you to test samples such as tungsten, which readily oxidizes above a few hundred degrees and forms a very thick tungsten trioxide on the surface. And this is a Nanotest Extreme system, slightly different to our standard system, but the same basic principles. And we've used this to do indentation tests, as shown here, in showing tests at different loads on a polycrystalline tungsten sample at 900 degrees. And you can use this again to pull out the mechanical properties as a function of temperature. In this case, this is the hardness from similar tests. And you can see it's non-linear on tungsten. That shows it's very difficult necessarily to predict. So if you just had even these 2 measurements, it would be difficult to predict what was going on here. So it's really beneficial to be able to test over that entire range. And that's what the Nanotest Extreme gives you. As you go to higher temperature on these systems, you get a more increasing time-dependent deformation. So this just shows what happens during a 30-second hold at these different temperatures from 750 to 950. And we can see there's progressively more creep at a higher temperature. We've also seen this in our standard Vantage systems. In this case, we're using a cubic boron nitride indenter and an argon purging environment to restrict sample oxidation, and also to work above the oxidation temperature of 500 degrees for diamond. And this is looking at a solid oxide fuel cell material. And what we can see is that it doesn't creep at all at 25 degrees. It doesn't creep much at 550, but then over that range, it dramatically improves. It increases its creep. So this restricts its performance. And this is a similar sort of thing now. This is higher temperature work on a bond coat from a thermal barrier system. So we looked earlier at the thermal barrier coating system. I talked and said about how we were able to protect this nickel-based superalloy substrate from the very high temperatures. And in between the 2 things, we have a bond coat system to make sure that there's decent bonding. And this M-Crowley bond coat is its mechanical properties also need to be optimized at high temperature. And what we can see here is that it's a very, very creep resistant material. So at 500 degrees, it creeps actually in this case even less than at room temperature. So it's really remarkable. But 700 is about its operating limit, and by 1000 you can see there's a transition to a much higher creeping behavior. And you can pull out mechanical properties as a function of temperature on these things. So as I say, the hardness stays reasonably constant and then drops dramatically. And you can see this bond coat particularly, it's dropping more rapidly here than the superalloy. And this is the sort of thing that people need to understand to optimize their material behavior. So high temperature testing is getting to higher and higher temperatures since our customers are producing more and more data at these very high temperatures. Typically, our customers in Arcon are doing an awful lot, Oxford University, MPL, a range of different customers around the world. So this also maybe should just say that this is our Nanotest system. So these pluses are Nanotest, and you can see how it essentially dominates the high temperature market compared to the competitors because it has this enhanced thermal stability. So just to sum up, hopefully I've given you an idea about how to reinforce Andy's message about nanomechanical testing being a very reliable technique to characterize the mechanical properties of advanced materials, how we can look at that at very small scales and really get out properties that are sensitive to individual phases It was described earlier about anisotropic materials in one of the questions. So we can pull out the different mechanical properties of the different crystallographic orientations, for example, just by indenting those different the surfaces of those different crystals. The main part of this talk was really to emphasize that material mechanical properties are sensitive to the test environment. So I gave 3 examples. Humidity, where we showed that the advantages of putting clay into these polymer nanocomposites was much more beneficial in high humidity environments. In impact testing, I showed you how it was really a combination of the mechanical properties and the microstructural factors that control impact resistance in these advanced coating systems. And in high temperature testing, I showed how time-dependent deformation was increasingly important at higher temperatures. Okay, thank you very much.
Up here on stage. Thank you, Ben, for that. It's very interesting. Again, let's take some questions as they come up from the questions that were submitted during your talk. If we can do those for 5 minutes, and then if we run over the 5 minutes, we'll catch up again at the end of the session. So yeah, question from Gabor. Very good question, actually. Can I use a nanoindenter to follow a MEMS cantilever bending? He's suggesting perhaps with a flat punch.
Yes, I think for silicon cantilevers have been bent by indentation with Berkovich's. So, but I think a small flat punch is probably better, because essentially what you want to be doing is not indenting while you're looking at deflection. So for those applications, typically you're looking at deflections. So you have the range of different geometries and test materials. We didn't really touch on test materials. I didn't really touch, but some of the material I showed at the end of the talk as well was on moving away from diamond towards sapphire and cubic boron nitride materials, which have better high temperature inertness.
We have some papers with cantilever bending in general, don't we? Even cantilever imaging at high temperature.
Yes, we do. I mean, that's
bone rather than.
I glossed over it a little bit, but one of the reasons why the system is so good at this mapping and targeting is it has the option for an integrated nanopositioning stage. So that integrated nanopositioning stage can be used throughout the entire temperature range. So that's the sort of stage that people like the University of Oxford and National Physical Laboratory have used to target on individual phases, and also to do their mechanical property maps, and to target exactly where they want to be on these cantilevers. Yeah.
Very good. So there's a question from Edgar Manuel. He has made an impact test in his latest paper. I think this is the group from Portugal, around Coimbra and Minho. That's that area. And the question is, I was trying to simulate coin minting damage in chromium nitride PVD coating. In your opinion, is it better to have a shorter or a longer off time?
It shouldn't make too much difference if you're doing an on-off. I think typically the 2 seconds on, 2 seconds off is perfectly adequate. We've run things at high temperatures as well, and in that case, you want to minimize any drift, then you can go to shorter times, but in decreasing shorter on time and off time. But essentially, it shouldn't make too much difference. What we didn't really discuss in the technique was in an impact test, the fact that it's the energy that controls what happens. So essentially what you do is you set the force, but you also set the accelerating distance, and you have those 2 parameters to play with. And that's one of the things we've explored with our new micro impact thing. It gives us a lot to access much higher energies, and then we can change the different probe geometries as well. So we typically moving towards spherical geometries. So, but the application is one that it's normally quite good for. So
it's worth mentioning we have done that application ourselves, haven't we, Ben?
And yes, we have done that application.
Exactly that. Yeah. So,
for an industrial customer. Yeah.
Very good. I'll go back and pick up one more question, and then we'll hand over to Adrian. So I picked up last one when I was scrolling up was from Lothar. It says, I'm interested in the characterization of sealing materials with rubber compound, but there is no chance to polish them. What is the biggest roughness you could accept?
I think it depends on the type of tip you use and what the sensitivity and what low depths you're prepared to get your information from. So to some extent, you've got rougher samples. If they're bulk rougher samples, when you just indent deeper to beat the roughness. So one of the things about the nanotest, it has this very accurate loading ability on particularly soft samples. So I noticed one of the questions we'd set people in the thing earlier actually didn't seem to have one right answer. It had several right answers.
Yes.
So that was
well, we're going to come on to that at the end and just explain that some of the answers are opinions rather than the answers. It's very much in keeping with nanoindentation sometimes. So there's I think I am for the formal reply. I think answer I amended it to reflect that. I know the question.
Okay.
But unfortunately, the one we put up here was the original question that was drafted. But yes, it's there is one in particular.
Should we hand over to Adrian now?
Yeah, let's hand over to Adrian. We will. Adrian Harris has worked with us micromaterial for the best part of 20 years, and he's going to talk about some of the tribology applications, both in the nano and the micro range. I guess my first question, Adrian, and as we start would be what's the difference between nano and micro? But you might cover that anyway. And Adrian's works on the application labs and works and consults with many customers around the world in collaboration. So some of you may know him from that. So I will hand over to you, Adrian.
Okay, thank you, Chris. I presume you can hear me.
Yes,
well, thanks for the introduction. So the difference between nano and micro, just to answer Chris's question before we start, is merely the scale we're working at. So we can perform tribological measurements on layers. If we think about a coated system, which could be in the order of tens or hundreds of nanometers thick or tens of microns thick. So whether we're talking nano or micro tribology basically depends upon the nature of the sample that we're working on. So what I wanted to do was just introduce the concept of nano and micro tribology, and I guess initially just what tribology is, and the techniques that we can offer with the Nanotest Vantage system. So tribology is a word that most people out there in the greater world are unfamiliar with, because it's a relatively specific and relatively new term. So it's the study of friction and wear, and the word tribology comes, I think, originally from a Greek word tribos, which means rubbing. So the term tribology was originally coined by a British engineer called Peter Jost in 1966. So as I said, it's a pretty new word and a pretty new science, but it's a very important science. And if you think about engineering systems around you, cars, aircraft, whatever out there that's got moving parts, then tribological failure can occur. And just thinking about the UK economy, the time of coining this term, tribological failure accounted for something like 1.5% of gross domestic product. So it's a big topic. If you can make improvements in tribological performance of materials and devices, then it's economically a very, very sensible thing to do. It's a complicated thing to do because the range of materials out there, which can be in sliding contact with one another or moving dynamic contact with one another, is enormous. So, polymers, ceramics, etc., metals, is very, very broad. But the environments in which they're contacting one another is also broad. Could be anything from vacuum to full liquid submersion, high temperatures, low temperatures, whatever. The nature of the way that the surfaces are loaded together, so particularly things like contact pressure, all of these things really come together to define how well a tribo system will work and how long it will be before it fails. So traditional tribological techniques, things like pin-on-disc tribometers, they're very good for comparing perhaps two sliding systems with one another. So you could take two samples of different surface treatments and put them on a pin-on-disc tribometer, run them until you see a significant event in terms of friction, and you can determine which of those coatings or surface modifications behaves better. But perhaps what it doesn't tell you is exactly why one behaves better than the other. And nano and micro tribology helps us to do more highly specified tests to try to understand why one sliding system perhaps performs better than another, and gives the engineer something that he can feed back into a development, he or she can feed back into a development process. So similarly to indentation testing, there's this the drive to make things smaller, and this basically follows technology. So over the years, of course, we've seen the advent of things like CVD and PVD coatings, and measurements of things like hardness and elastic modulus of those coatings has necessitated smaller scale testing. So traditional Vickers hardness testing or micro hardness testing is no longer really sufficient. So we've had to develop techniques which work at smaller length scales, where indentations are basically so small that they are optically invisible. So we can keep our deformation zones contained within our coating of interest. And tribology follows a similar path. So, if we're using a macro scale pin-on-disc tribometer to try to study the tribological performance of 100 nanometer thick amorphous carbon coating on a piece of silicon, then perhaps we're not going to learn very much from that technique. So we need to develop new techniques which are more specific to the length scales that our samples come from. Excuse me. So just like to introduce the concept really of why we do nano and micro tribology. And of course, I think an important term to think about here is single asperity tribology. So if we think about two surfaces which are sliding together, we can consider them as having a complete contact area, and we could say, well, the contact pressure between those two surfaces is merely the load, which is pressing them together, divided by the nominal contact area. But in reality, of course, when we zoom in on the surface, what we realize is that in fact that nominal contact area is a gross overestimation of the actual contact area, because our contact is actually comprising of many thousands, millions in reality, of small asperity contacts. And the contact pressure at those asperity contacts can be very, very high indeed. And it's damage that occurs at those localized contact points which actually gives rise to frictional interaction between the surfaces, and also the onset of failure, tribological failure. So what we do with nano and microscale tribologies, we actually try to simulate what's happening at a single asperity contact. So we use a small tip. We don't necessarily use very high loads, because the tip radii that are available to us can be very, very small indeed, less than a micron radius. And we can actually load these materials well beyond a yield point and actually drive failure in a single pass or a few number of multiple pass scratch or wear type tests. So that's the origin of it. So what we're doing is we're actually trying to focus on the origins of friction and wear, okay, themselves. So just along the same lines, this is some sort of reflected light sort of observation of two surfaces together. So if we imagine the black rectangle there, I don't think you can actually see the cursor as I'm showing the slide, unfortunately, but the black rectangle there is the nominal contact area, and the colored regions, the red and the green, a little bit of yellow, they represent, in terms of a pressure scale, the actual contacts. Okay, so you can see that the actual contact is a very, very small proportion of the nominal contacts area. So, you know, we can see there that you've got regions which are 2.5 megapascal plus. Some regions much, much higher than that, going up to 20 megapascals. So, so these localized points, when they start to fail, will lead to the onset of a tribological failure at a larger scale. So, just to put it into some context, as I was saying, you know, we can look at relatively large areas with traditional techniques, and here's an example of that. So let's think about an acetabular cup and ball type joint, so a replacement hip joint. It's a pretty big ball, okay, and so nominally the pressure at the contact of the ball and the cup is pretty low. But if there's any contamination, whatever in that joint, any kind of asperity type contacts, then we will get localized damage, and that will seriously impinge on the lifetime of a joint. So, you know, they're designed to last, you know, between 1 and 2 decades, but in reality, you know, it's quite well publicized, of course, that we hear about many premature joint failures. And of course, you know, the joint manufacturers do work very hard to improve their technologies as much as possible. But of course, as soon as we start talking about bioimplantable devices and failure, then of course it can become a very litigious area. So the pressures to further improve the material performance are enormous. And so how can nano and micro testing help with this? Well, if we take a look at an actual hip joint, ball joint surface here, you can see these scratches in the surface. And here we've got a scale bar, 10 micron scale bar. So what you can see is we've got scratches in this surface from a recovered failed hip joint, which are at the scale of the types of scratch tests that we would perform, or wear tests that we would perform using a nanoindenter or a nano scratch test device. And so the fact that we can actually produce in a controlled way damaged scars of this kind of scale, and we can actually combine that technique with measurements of friction on the indenter tip, and we can combine it with the environmental control to simulate the in vivo conditions that the joint lives in, means that we've got a pretty powerful tool in our hands for starting to simulate what may well happen with different materials in the body environment, in that dynamic tribological environment. So the instrument that we use for this work is the same as the one really that I think Ben and Andy have introduced for other applications earlier. So it's a multifunctional tool called Nanotest Vantage, and you've already had introduced to you the concept of instrumented indentation. I'm not sure whether impact and fatigue was introduced, but really this talk is focused on these guys here. So nano and micro scratch and wear testing, nano fretting, an option called the nanotriber test, which we'll look at a little bit later, and the fact that we can combine it with these various environmental conditions. Okay, so it's this multifunctional tool that allows you to mechanically characterize materials in terms of fundamental mechanical properties, and also then to perform highly specialized studies to replicate application conditions in a tribological perspective. So we have a range of techniques, as I mentioned on the previous slide. We have scratch and wear testing, fretting, and the triber test. So why do we have a range of techniques? Well, it's because they cover between them different types of contacts which can exist in the real world. So nano scratch testing, first of all, the contact pressures tend to be very high. If we're talking about a coated system, what we try to do is to dimensionalize the test. So that means to select an appropriate tip radius, probe radius, to get a maximum stress position somewhere close to the vicinity of the coating and the substrate interface. So often what people are interested in there, often what happens in a tribological system is you get a detachment of a coating material from a substrate. So that's to say that the coating itself doesn't necessarily fail, and neither does the substrate, but the interface does. So that's one of the major things that scratch testing is interested in. The scratch testing, we tend to use, as I said, fairly small probes, so 5 to 25 micron probes. So 25 tends to be more something we'd use in micro scratch testing. The instrument load ranges are very wide. So we have on our low load head up to 500 millinewtons, and then we have a high load head that takes us to 30 newtons. And so the combination of the correct load range and probe size is a key thing to get right when designing a scratch test. Sliding speeds tend to be low, and track lengths for the scratch also tend to be small. So a millimeter would be regarded as quite a long scratch. Okay, we can do a single cycle, so normally that will be a ramped load scratch test, or we can do multiple wear tests where we use a subcritical load multiple times. And so typically we might go up to 20 cycles. So it's a small number of cycles, a small distance, but high contact pressure loading, so small tips and can be quite high loads. And of course we measure friction, and we can also measure additional tertiary signals as well, which we'll cover a little bit later on in the talk. So next slide. Another technique is nano fretting. So fretting is a lower pressure test, okay? Still a small track length, okay? But many cycles. So where scratch testing was 1 to 20 cycles, we can be talking about 1,000 to 200,000 or more cycles in a fretting test, but a small amplitude. So here we're talking about up to about 20 microns. Okay, so here in this test, it's a reciprocating wear test. The probe will be sliding backwards and forwards rapidly, high frequency over the same track length, and that simulates a different type of real world contact scenario. Okay, so it's not an overload test like scratch testing can be, ramp load scratch testing, loading up until we get a failure. It's a subcritical loading, and it's more of a wear and fatigue type test. And then we also have a thing called the nanotriber test, which is also a reciprocating technique, rather like fretting, but critically over a longer scan distance. So 1 to 10 millimeters would be typical. We can go longer than that, up to about 40 millimeters, in fact, but in most cases, there's no need to do so. Using the same type of load ranges and using larger tip radius probes. Okay, this again is more of a wear type test. It's essentially like a slightly scaled down, more conventional, traditional reciprocating tribometer test. And again, we measure friction as well as probe depth, and we can measure other secondary and tertiary signals as well, such as electrical contact resistance at the interface of the probe and the sample. Excuse me. So scratch and wear testing, so high contact pressure, low cycles, and a small number of cycles and short track length. So there's a couple of micrographs there. Here we've got some ramped load scratch tests. So there are 5 repeat tests here, actually scratched in this direction across the sample. And what you can see is a little bit of plastic deformation here up until this point where you get this great big delamination of the coating. So remember I was saying about trying to position a stress maximum so that you can actually fail the interface of the coating and the substrate. So that's a single pass ramped load or increasing load scratch test. Another type of test, which we would call a scratch test, is a multiple pass wear test, where we would scan over the same path multiple times, okay, using the same subcritical load. And subcritical is taken to mean a load which would not drive a failure in a single pass, okay. And so what type of things can we do with those? Well, this is an example of a 3-pass scratch test. So it's a thin tetrahedral amorphous carbon film on a silicon wafer that we're looking at here. And what we've done is a 3-pass scratch test. So for the first scan is we scan along our intended scratch path with a low contact load. Okay, so maybe we'd use something like 0.1 of a millinewton or something like this to just produce a topography of our initial sample surface. Then what we do is we do our ramped load scratch, and this is our ramped load pass here. And what's happening is as the load increases, the depth increases. We can see at a certain point an event occurs. And at this point, we don't really know what that event is, potentially. You know, you can see that something's happened, but we need to wait until the completion of the test to get a full picture. So the final pass, the third pass, is another low load topography. So we do a low load topography before our loaded pass scratch, and we do one after the loaded pass scratch. And so this line here is our post-scratch topography, okay? So we can see now, when we've got all those various data sets together on one chart, we can pick out some events and we can match that up with our microscopy. So we've got our big event here, which we saw during the loaded pass scratch, and we can see a corresponding big step in our post-scratch topography. And that's basically complete film removal. So, you know, the sample is destroyed at this point. Basically, we've gone through the coating. We're now down to the silicon substrate. But there are some events that occurred before that. So if we go back to the first event, just here, this LEP, this is really the transition of our contact from fully elastic to elastic plastic. So we called it load elastic plastic. And what you can see is that pre and that post scratch topography trace actually separate at that point. Okay, so until that point, our contact was elastic. On load, you know, we had a total measured deformation which was thicker than the coating. So the sample had elastically flexed to, you know, something in the region of 100 nanometers, but that was completely elastic. But anything beyond that, we're into plasticity. Okay, and then we see this other fairly clear transition point here, quite a major step. And this is where we start to get some film removal behind the probe. We see it's behind the probe because we see no corresponding event in our loaded pass. So during the loaded pass of the scratch test, there's no obvious sign here of anything happening. But when we do that post-scratch topography, we can see that we've actually started to achieve some film removal. So there's a step here. So that's telling us really that we've got some kind of failure behind the probe in this case. That doesn't always happen. It depends on the nature of the sample. So that's what a ramped load scratch test looks like. Along with this, we would also have a friction data set as well. And we would certainly see at this point here some quite major events in the friction signal. So you can combine ramped load scratch testing with other techniques as well, so other instrumented signals. And one of those is acoustic emission. So this is a scratch test on a silicon carbonitride coating using a 10 micron radius diamond probe. So it's a rather nice SEM image here of our scratch track. And if we take a look at this, we can see some cracking that commences about here. Okay, and during from our indentation system, from our scratch test data, our depth and friction scratch test data, this is pretty much where we see an instrumented initiation of failure. But the question is that really the onset of failure, or is there something happening beforehand? So we can combine the system with a high resolution acoustic emission sensor. So point B is corresponding with this point here. Okay, so this is where we could see a failure happening and we could see something on our scratch test data. But our acoustic emission sensor tells us actually that a failure is occurring a lot earlier than that. So here we've got events, crack events, which are so small that we're unable to detect them through friction change, or we're unable to detect them through a depth change. But through an acoustic emission sensor, we can pick things up much, much earlier. Okay, so you've got a range of instrumented signals that you can use in conjunction with one another to get a full picture on what happens during your scratch test. So this is a multiple path wear test, and so this is quite nice. It shows a comparison of 4 different samples. So these samples are similar to one another in the sense that they are the same coating material on the same substrate, but they're different in the sense that the bias which is applied to the substrate during the deposition process is different. So, you know, here you've got minus 20 volts bias applied, and here minus 80, and various levels in between. And in indentation, actually, there's a difference in the hardness and elastic modulus of these coatings. You know, this coating is actually the hardest out of these 4. This one's the softest. So, you know, if we go back to this kind of man on the street understanding of tribology, and we said, well, we have a hard coating here and a slightly less hard coating here, man on the street who doesn't know much about tribology would probably be forgiven for saying, yes, well, I'd expect the harder material to exhibit a better wear performance than the softer material. But in reality, we as material scientists perhaps have a little more understanding of the fact that in the world of materials, we can't get something for nothing. And what this multiple pass wear test has actually revealed to us is that despite this being harder, this being softer, we have achieved that at the sacrifice of the interfacial bond strength between the coating and the substrate. So here, in 5 repeat passes with the minus 20 volt bias applied to the substrate, we get a little bit of edge cracking, but we can't see any exposed substrate. But as that applied bias increases, what we see is larger and larger and larger interfacial failure between the coating and the substrate, incrementally extending to incrementally larger distances away from the scratch track itself. So that's something which really you would certainly not be able to predict from indentation alone. And it's not something, I think, which would show through in any kind of, let's say, traditional tribological test that you might choose to perform on these samples. So what happens in a multiple pass wear test? Well, this has got a nice example. So it's actually a test of a 1 micron diamond-like carbon coating, and it's a 20 cycle test. So what we've done is we've been using a 1 millimeter long scratch bar. So this is distance along the scratch track here, and this is a frictional force acting on the probe. And we're applying a normal force of 70 millinewtons to the sample via our probe here. So what we do is we don't want to shock load the sample, so we ramp the load up. So the period of the test that I'm interested in is when I reach my 70 millinewtons maximum load. So here we're kind of joining the event at the 13th repeat scratch of 20. And what we see is this pretty stable frictional force acting on the probe at about 8 millinewtons. Okay. When we then look at scratch 14, we see a small step in friction. So maybe there's an additional, you know, potentially 1/4 of a millinewton force acting on the probe there. You know, that could be something or nothing at this point, but let's go to scratch 15. Oh, well, you know, it's developed. So now we've got a major failure commencing. We've got delamination, a partial delamination of the coating from the substrate, and by track 16, scratch 16 rather, the whole track is destroyed. Okay, and so we can actually produce quite nice wear evolution charts in terms of mean depth of the probe versus scratch cycle number for multiple different samples, and compare how well they perform in a sliding scenario. So fretting, moving away from scratch, moving to fretting, as I said before, it's more cycles, a greater number of cycles, so thousands to tens or even hundreds of thousands of cycles, small amplitude, and critically, I didn't say any lower contact pressure as well. And so this gives you an idea of what we're talking about here. So this is these are some friction loops. So as the sample is moving back and forth, so the sample moves from one direction to the other, we go into a constant sliding period, and then the sample goes the other way, round and round and round. So the area inside these loops is actually an energy, okay, frictionally dissipated energy. And here we've got friction loops at different applied loads. So you can see from this chart we're talking about in the region of 20 micron track length, okay. And so this technique called nanofretting fills this gap between AFM-based tribo testing, which is obviously, it's a valuable technique, but it does reach limitations when you start to get to coatings which are much more than a few tens or hundreds of nanometers thick, and conventional tribometers which work at a scale which is too large. So the fretting techniques drops nicely in that gap where previously there wasn't an instrumented suitable technique. So this is what wear tracks look like. So these wear tracks are about 15-20 microns length, and these are on some different biomedical or biocompatible metals. So these are metals that could be used in hip joints, for example, as we looked at earlier on. And what we're doing here is we're just looking really at the visual difference in those wear tracks as a function of load and for three different materials. And what you're seeing is that some of these materials behave very well in terms of very, very small amount of debris outside of a wear track on this titanium 6-4 here. But then at the higher loads, it's probably the worst in terms of debris production. The stainless steel at the low loads looks pretty poor in terms of the quantity of debris that's actually removed from the wear track. But comparatively, its performance has remained relatively stable across the load range. So we can start to assess pressure and environment and load cycle number sensitivity of these materials together. Okay. So this is another example where we've looked at a thin amorphous carbon coating on a silicon wafer, so it's 150 nanometer thick layer. And we've done fretting tests at two different amplitude scales. So at the low amplitude, we're talking about a 2 micron oscillation, and we're using 200 millinewtons to apply this. This should say micron. I don't know why this has got changed here. It's 150 micron radius ball. So what you can see is the ball was pressed here concentrically of this circular site. And what you can see all around that site is this eroded ring of material. And that's basically because under these contact conditions, remember this is 150 microns, 150 micron radius ball with 200 millinewtons applied, we've essentially got a static contact. What we've done is we've elastically moved, oscillated that contact point around backwards and forwards, and we've driven kind of an erosive fatigue type behavior around that contact point. Okay, so 72,000 oscillations to get us to that point. And in this test, what we've done is we've reduced the contact load. Okay, so now it's going to be easier for the ball to slide relative to the surface, and we've increased the amplitude of oscillation, and now we're getting a full gross sliding type contact. Okay, and you can control your amplitudes from anything in between. And an interesting point to go to is an amplitude where you get some sliding, but you don't fully expose the wear track, and you can actually then end up with trapped debris, which works as extra abrasive particles. You get this kind of third body erosion type test, which accelerates wear rates further. So you can simulate again a large number of real world conditions by adjusting your test conditions accordingly. This is what output data tends to look like from these tests. We don't just assess performance in terms of visual of the wear track itself. So here we're looking at a 1 micron carbon coating on a silicon wafer, and a test which is 18,000 seconds long, so it's a long duration test. We're oscillating at, I don't know why we chose exactly 53 hertz, and just did basically, and a 22 micron track length. So the sample is oscillating back and forth 53 hertz with this probe applied with 50 millinewtons, 10 micron radius contact. And what we see is a change in displacement over our test duration. So over the first approximately 9,000 seconds, so that's quite a long period of time. It's in the region of 2.5 hours, something like that. We see a sudden increase in the depth of the probe, okay, which corresponds quite well to the 1 micron coating thickness that we're talking about, okay. So at about 9,000 seconds, we get that failure event. And then that stabilizes off, and the contact area has increased a little bit, so the contact pressure will have gone down slightly. And then we're getting some what looks to be like some kind of stick and slip type events in the silicon substrate. Okay, so we're building up a lot of failures, and actually it took nearly 500,000 cycles to drive that failure. Okay. So the nanotriber test, this is the final one of the techniques I wanted to introduce. So lower contact pressure, medium cycle, so tens, hundreds, maybe a few thousands of cycles. We're certainly not going to hundreds of thousands of cycles, and a larger amplitude, larger oscillation amplitude. So like all of these techniques, we're using the same loading head on the instrument. That's to say we're using the same loading heads as we use for indentation or for impact testing or any of the other techniques that we can achieve. It's worth saying we can do these tests with the high load and the low load head. Here we've got a test set up with our low load head, and this is our nanotriber test stage. And this stage will actually allow us to oscillate the sample in this sense, back and forth, laterally with respect to the indenter. We can actually do tests up to 40 millimeters in track length, although we rarely in practice would do that. We are able to combine that with additional techniques. So we could even do this in a fluid. We could do this with, for example, the sample could be an electrical connector, and we could pass electrical charge between the probe and the sample and look at how the electrical contact resistance changes as the test progresses. So these are what data looks like, just a few screen grabs here. So this is time of the test along here, and these are our friction cycles. So these are our friction loops we're going. That was sliding along, then the other direction sliding along, okay? And we can turn these into friction loops. This is a macro scale of the whole frictional history of the test. So lots and lots and lots of data, and what we can do is we can actually position cursors along our full data set and zoom in and look at individual sliding cycles. And then we can choose regions we're interested in. We can export those and replot them, work out frictionally dissipated energies, that sort of thing. And so here what we've done is we've run a test on, these are actually some electrical connectors, and we've plotted here the frictionally dissipated energy in microjoules as a function of the cycle number. And what we see is on 3 repeat tests are fairly consistent between 40 and 60 cycles. We suddenly see an increase in the frictionally dissipated energy, and that's a strong indication that our tribological contact is breaking down. You can see then from that point on potentially the frictionally dissipated energy is gradually dropping again, and that's as the original surface of the material has been removed, worn away, and we're now deeper down into the sample, and we're potentially now polishing a little bit that contact, and consequently the frictional force is reducing, the frictionally dissipated energy per cycle is reducing as well. As I said, we can combine this type of technique with additional signals. So what we've actually done here is we've used an electrical connector, and we have used an electrically conductive probe. And what we've done is we've asked our electrical contact resistance system to maintain a fixed current flow between the probe and the sample. So we could say, well, I want you to flow 0.1 amps, for example, between the indenter and the sample, and I want you to vary the voltage to keep that current flow constant. And what we see in these tests is, at the same time as we see our frictional dissipated energy increasing, we see the required voltage to maintain the fixed current target, we see that start to increase as well. So it's a good indication that we're having a tribological type failure of our coating on our electrical connector, the gold coating on the electrical connector, which is responsible for the low electrical contact resistance of that connector. So these are useful for things like sliding electrical connectors of the type, for example, that you might use to charge up a mobile phone. I think we've probably all had the experience of, after some time, some unreliable contacts between our phone charging cable and our phone. And basically, in most cases, that's due to the external highly conductive, usually gold layer on those contacts wearing away. Just to mention, in terms of probes, we can use whatever we want, right? So long as it's electrically conductive for these tests. So you could use a boron-doped diamond indenter. I mean, just standard diamond is not electrically conductive, but let's say boron-doped diamond is available, and that is electrically conductive. Or you could use metallic probes, and the system is very flexible in terms of what you can use as a test probe. So that means that if you have a very specific tribo system that you want to replicate on the instrument, then that is possible, or more so than it is actually on some competitive instruments. So onwards, it's worth mentioning as well, there is a micro nanoscale pin-on-disc tribometer as well, which works in a similar way, other than that the sample actually rotates rather than slides backwards and forwards. Okay, then I just want to show one more slide, which is just talking about performing tests in application-specific environments and other compatible techniques. I rather hope this would come up as an animation, but unfortunately, the platform we're using, it's not so easily possible. So, of course, we can perform tests at elevated temperatures. It's given that not all tribo systems work at ambient temperatures, and so we can increase our sample and probe temperatures to suit the reality that we're trying to replicate at the lab scale. We can drop the temperatures as well. We can create potentiostatically controlled or galvanostatically controlled corrosion cell or plating type environments by using a potentiostatic galvanostat in a liquid environment. So we have a liquid cells available. Of course, the liquid cell can be used without the potentiostat or galvanostat as well, just to perhaps provide, in the case of a bio application, you may want to submerge your samples in synovial fluid or something like this. So that's possible. You could potentially also perform tests in an oil lubricant or something like that, depending on what's appropriate for your reality. You could change the gas environment if it was appropriate. You could do the tests in a vacuum. We do offer a vacuum nanoindenter. I think Ben introduced that briefly earlier on. So that is available. The same techniques as are possible in ambient conditions are possible with a vacuum system, and we can also use that vacuum system and other purge systems that we can offer to exchange the air out with alternative gas if that's important in the replication of the tribo system. We mentioned the acoustic emission system as well. Very, very highly sensitive system, which enables us to get an earlier view on the earliest onset of failures. And of course, we mentioned this electrical contact resistance system, which uses this source meter system to maintain either a fixed voltage or a fixed current across the contact of the indenter and the sample. So in summary, nano and microtribology gives us access to things which are not accessible from, let's say, traditional tribology techniques. So we get more than just how long it takes for something to fail. Particularly with the scratch testing, we can actually look at what is the first thing to happen? What's the origin of the failure? Is it a cohesive breakup of a coating, or is it an adhesive failure between the coating and the substrate, etc. We can learn a lot of things from that we can't learn from traditional techniques. The nanotest instrument offers a really wide range of techniques which we can engineer very easily. When I say engineer, I mean specify probe materials, probe dimensions, contact pressures, etc. We can engineer and design tests very quickly and easily to replicate a very, very wide range of nano and microtribological scenarios. It's multi-technique, it's multi-environment, and it's multi-scale. So not a completely exhaustive insight, but hopefully an introduction to the existence of these as techniques. And of course, if anybody's got any specific questions they'd like to give us either now or they'd like to give us, after this session, then we're very happy to answer those. Thank you.
Thank you, Adrian. Appreciate that. I suggest we now go through. All of the questions that we got. My camera's now off again for some reason. I
can see you.
You can see me, can you? I can't see
yes, you're there.
Okay. Yeah. Good job. I'm behaving myself then, I guess.
Ben's with you as well.
So let's. There's one question that came in Junior Talk, so we'll take that first, and then we'll just go back up to the top.
Yeah.
So the one that came in during the talk was friction and wear are system parameters and very dependent on test conditions, e.g. the materials of the tribo pair. In nanotest, the probe is usually diamond, but in macrotest, the tribo pair is often not diamond. How well do nanotest results correlate with the macrotest, and can we relate them?
Yeah, okay. Well, the first thing is I guess the question may have been asked before I said later on in the talk that, of course, you're not limited to using a diamond probe. I regularly use steel balls if that's appropriate for the application, or even polymer contacts. So, if there's a specific material pair that you're interested in, then the nanotest is a very, very engineerable system. It's very easy to make a probe actually to use for these tests. Okay, so typically if we're looking at a scratch test where you want to interrogate the response of the coating and the substrate together, then a diamond probe is a very wise choice indeed, because we can pretty much guarantee that the diamond probe is not itself going to deform, fracture, break in any way at all. So we're actually forcing that sample system to fail. But if it's friction that you're interested in measuring, then of course, the frictional coefficient is a function of the two materials that are sliding together. And so the frictional coefficient that you might measure between any given sample material on a diamond probe and any given sample material on a steel probe, for example, could well be very different. But as I said, I mean, so long as you can, you can mount your sliding, your static partner, as we call it, on the loading head side of the instrument, As long as you can mount that somehow on a 1 millimeter diameter pin, you can put that in the instrument and use it as a probe.
Very good.
Yeah, and NPL have also looked at this sort of stuff. So there's normally quite good correlation, particularly when the sort of ploughing contribution, which is going to be the same in, just with the harder material, so the ploughing into the softer material, if that's the dominant component on the friction and wear anyway, so then it tends to correlate quite well.
Very good. So if we go back to the questions we couldn't answer earlier, we'll try and get through everything as quickly as we can. I would also point out that on your screen, probably on the left-hand side as you look at it, there will be windows coming up. The next one, I think, will be the link through to the website where two things will happen. One is you'll be able to get the answers to the questions that we put up earlier. And as I mentioned earlier, some of them are some of the answers are our opinions. So we think best answer. And also the circular attendance will be there. And it'll if you ask you to input your name and a couple of fields at the start, and then they will appear on the certificate. So if you don't put your names in, you won't get the certificate with your name on. That's the reason for asking the questions at the start. The next question is from Jithan. Is there any criteria to determine whether A, to fix the load, or B, to fix the indentation depth for analysis?
It depends what you're testing, what you're trying to achieve, really. So if you're working with, say, hard on soft systems, so something like a titanium nitride coating on a piece of tool steel or something like that, then this very approximate rule of thumb, which appears in the ISO standard, where you're advised not to exceed 10% of the coating thickness, is something which is worth thinking about. Okay, at a certain point, you can indent too deep, so as to no longer be really measuring your coating only properties. You're starting to measure a composite response of the coating on the substrate. So in that case, you need to be mindful of how deep the indenter is going as a function of the coating thickness. You can define your tests with the instrument to terminate at a specific depth if you want to. Or you could do a few trial tests and work out how much load you need to go to that depth and run tests in a load controlled way. So yeah, it depends on what you're trying to achieve from the test, really. But the scenario I just outlined is probably one of the most common things people do with nanoindenters. And yeah, I mean, being mindful of the indentation depth is important.
So that's one side of it, and the other side is if you're interested in particularly in creep properties, then it's usually a good idea to fix the loading time prior to looking at the creep period. So that's more easily done by fixing the load and controlling that rather than the depth. So as Adrian said right at the beginning, it really depends on the application which one you want to do.
Yeah, it's one of those ones that the question does need a case scenario background to answer it in the most helpful way to you.
Thank you. Okay, thank you. Just next question. ER is reduced modulus. ES is Young's modulus.
And EI is the modulus of the indenter, which is typically diamond, which is sort of about 1140 gigapascals as a standard value. As I say, we also use boron nitride and sapphire indenters, which have lower stiffness for high temperature testing in some cases. But so you need, from the experimentally determined reduced modulus, you need to then put in the indenter modulus to determine the sample modulus.
So the reduced modulus is essentially the elasticity of that contact. It's the modulus of the contact. So both the indenter and the sample are deforming, and so what the instrument's measuring is the response of the pair of those materials together. And as Ben says, if you know the thing you need to unlock the situation is the Poisson's ratio of the sample. If you know the Poisson's ratio of your sample, you can very easily then convert your measured reduced modulus to Young's modulus.
Very good, thank you. Yeah. So I'll also point out on the screen there's an advert for the next seminar that we do, that we're doing. This is on high temperature, specifically on high temperature nanomechanics, so contains a lot more information to a higher level. So if you've found the high temperature nanomechanics portion of this interesting, then I do recommend that to you. The next event is much later in the day, so 5 p.m. UK time. Of course, recordings are available and will be sent out to anyone who registers anyway. So if you end up not making it, you will get you will be able to, well, you will get sent a copy of the recording. I would also stress that if you do like these sort of seminars, the best place to find out about all the seminars that we're doing is on our LinkedIn page. So if you go to LinkedIn and just type in micromaterials with a space, I believe, I think I'm right there, then it'll take you to the micromaterials LinkedIn page, and you can follow that. And that's used for announcing these talks, but also it's where we put technical updates, so links to new papers and such like. It's not used for marketing messages, or not bland marketing messages about what a great company we are. It is very much on technical talks, technical papers, and technical updates. Okay, so let's go to so I would recommend LinkedIn. Yeah, go to our LinkedIn page. So the next question. What is the surface roughness limit to get a meaningful result with nanoindentation? What is the maximum sample skewness? Which comes from the metallographic surface preparation. How much can it deviate from 90 degrees? These are parameters which affect the results. How much? How do they affect the results? Ben, yes, ISO might have guidelines.
The ISO standard recommends if you indent 20 times the RA, you're completely free of the surface roughness effect. So if you have a bulk material like a superalloy, that certainly is one approach. In practice, it's usually better just to get the best finish that you can do. And particularly even as well, if you're depositing coatings, that surface preparation prior to depositing the coatings tends to produce a much better coating surface finish for subsequent.
It's the case that often we do use the integrated microscope on the instrument to locate suitable areas on rougher samples. You try and find regions where roughness is lower and place measurements at those locations. So it tends to be a bit more efficient than just carpet bombing the whole surface and trying to find the let's say the mean response, as it were. So,
but that is another approach as well. So if one of the main reasons to handle surface roughness is to get a large array of measurements, and when you have that large array of measurements, when you have the load displacement curve, then you have in it that relationship between the elastic and the plastic work, which allows you to interrogate whether any of your curves are particularly affected by surface roughness or not, and remove them from the set. And that's the main trick in our mapping approaches compared to our competitors, that we retain the entire curve set.
So the other bit, the sample skewness, there's a recommendation, I think, in the standard as well. It says 7 degrees. Now, I recently was dealing with some samples for a contract customer here, which were at 9. And it was certainly too far. We modified a sample mount accordingly to match it. But certainly it would seem that the 7 degrees is, it seems very, very reasonable as a limit to me. It's a lot when you look at 7 degrees, and it amazes me that you can still get meaningful values out at that angle. But like all of these things, and similar to as Ben said, of the roughness, it's basically as good as you can get, ideally. So if you're preparing samples in a metallographic mounting puck, then it is possible to machine the backside of the puck afterwards to make it parallel with the front side. That's sometimes worth doing. So again, it's one of those cases, the flatter the better. But if you're nearing that 7-degree limit, then you should really start thinking about some kind of corrective action.
Okay, let's move on to the next question. Can anode coatings be tested for its hardness? Because they do require inert atmospheres. So I think you could take that on.
Well, as I said, you can put a system in a purge chamber, glove box type system, and you can exchange the gas out with an inert gas, and you can run in there. If you've got something which is reactive with oxygen, then yeah, get rid of the oxygen. We've had some people working with lithium, for example. Now, lithium is obviously fairly exciting material in the wrong hands, and yeah, they use a liquid cell for measuring that. They actually do the measurements submerged in an oil liquid to keep it away from oxygen. How exactly you do the handling to get it into the liquid, into the oil in the first place? Well, that's going to require some ingenuity at the user level, I think. But yeah, we provide these various environmental control systems for exactly these purposes, to provide test environments which are suitable.
Yes, and vacuum as well, of course.
Yeah, vacuum is possible.
If it's for those, which is becoming more common. Okay, next question. Can we measure nano hardness of multi-layer coatings where each layer has a thickness of 5 nanometers?
That's certainly on the edge of what we can easily do. So we have certainly tested 5 nanometer thick tetrahedral carbon coatings and accurately got their hardness and stiffness. It's possible. The main issue is the sharpness of the indenter used to do the type of tests. So the sharpness of the indenter controls how big that plastic stress field is. So it would require a very sharp cuticle indenter to give you a chance. But there's also modeling approaches that allow you to extract information, even if you are over that 1/10 film thickness.
The things we're saying is that if you've got multiple layers, each of 5 nanometers thick, then distinguishing differences between them as you indent in terms of changes in depth as you go from one layer to another, I think that's pretty much out. That's not going to be terribly achievable. But yeah, as Ben says, there's a lot of additional information in an indentation curve, and this post-measurement computational methods have certainly worked very successfully for us when you're talking about coatings which are in the regions of a few tens of nanometers thick. It's certainly, as Ben says as well, we can perform analysis quite reliably based on the conventional unloading analysis that Andy introduced to you earlier on, and so the computational method serves as a confidence booster, really, that your measurements are in the right region, using the same data sets but 2 completely different analytical methods of the data sets.
The other way is possibly, again, to provide further support, if you've got a very, very precise surface tilt polish, if you like, so that you're removing different parts of the coating at different layers, then providing a test matrix across that area, that will give you information as well. But again, that relies on the user skill in doing that preparing that sample in the first place.
Yeah, we've certainly done that on thicker coating, with multi-layer coating materials. But as Ben says, yeah, the creating a suitably fine surface throughout the thickness, where you know, where you're going to be using an abrasive method perhaps to polish through with an abrasive particle size which is significantly bigger than the coating thickness is problematic, perhaps.
Yeah.
So.
Okay, let's move forward. Got a few more questions. We're well over time here. How can we use creep to define the property of a material?
Well, indentation creep is essentially giving it an idea in terms of the time dependence of the material. So it's you can relate indentation creep to viscoelastic properties, and you can relate it to conventional creep parameters. There are equations, so the applicability is still being discussed, but the equations are there to do it.
Okay. Yeah, let's move on. Then how can we know that indenter needs to be exchanged? Good question.
By continuing to test on reference samples at fairly regular basis. So if you have a few silica reference sample and you indent that reference sample with your indenter, and then suddenly one day you're indenting it and you find that you're actually going in a much smaller depth, then that is indicative of the fact your indenter is worn and it's transitioned to a more blunted geometry and it needs changing. It's that just good lab practice essentially to periodically check your indenter sharpness.
Good. Okay. Next question is from Bolla. How quickly we could perform property mapping? Speed is dependent on material or load dependent. And what would be the lowest load? So I guess yes. How quickly can we do accurate property mapping? Might be a good question.
No, we do grids of say like a few thousand indents in a few hours, that kind of thing. Okay.
Yeah.
So that's a sort of rate that we're talking about. That would be I think you had introduced perhaps, or we mentioned at least, this nano positioning stage. So what that allows is a very, very rapid movement of the sample from one indentation site to the next. Okay, in an indentation experiment, obviously there's several steps that take place. There's the indentation itself, and then there's moving to the next measurement site. The nano positioning stage allows that to happen instantly, and that's what really brings the testing time down. So instruments equipped with that can map much, much faster. But if you're then going to be you've then got to be mindful of your indentation size, because if you think you might have you might want to do a 50 by 50 micron map, so 50 by 50 microns, was that like 2,500 indentations, I think, then the indent will be a micron apart, and so you've got to be mindful of your Berkovich geometry, and therefore how deep you're going to go to prevent overlap of the indentation sites. So the indentation process itself could be as short as, a second or something like this. We could load in a fraction of a second and unload in a fraction of a second. And data acquisition rates can be matched with those contact times to produce, easily sufficient data for reliable analysis.
Yes, and the key thing is the reliability of the data, because you can indent very quickly, but very shoddily.
If you think what an indentation has got to do is, during an indentation process, you've got to determine at what point the indenter actually contacted the surface. That's really critical. I mean, if you get that wrong, then you don't know exactly how deep you've indented into the sample. So it's a fundamental thing you don't know that you need for your analysis of your data, right? You don't know the depth accurately. And so there is some doubt. There are some systems out there in the market which go just literally blindingly fast. But it does seem somewhat difficult to work out how they can actually determine an actual 0 point. So I think at a certain point, once you get beyond, say, a few thousand indents in a few hours, I think what happens is the technique starts to become what you might say semi-quantitative. It basically will tell you that it's harder here than it is there, but the actual reliability of the values starts to drop away a bit. Okay, so yeah.
So Let's go on to a question from Kareem next, which is another good one. What is the maximum dimensions for the sample we can attach?
Well, I've put on there entire 300 millimeter diameter silicon wafers before without cutting them. And then just last week I was dealing with a prospective customer who was got this running a general lab at his institution, and he says sometimes people come to me with quite big samples which I'm not allowed to cut. So he says maybe up to 150 millimeters thick, and so during a video demo we fitted a sample of that size to the instrument, so they can be thick, thin, massive, and whichever dimension really is important. I think we have probably one of, if not the most flexible platforms to accommodate unusual and large size sample geometries. So yeah.
Very good. And following on from that, same theme, Hibin asked, what's the minimum size of the sample in particular?
Well, I've got some samples.
Is it possible to use a crystal a few microns across?
Yeah. I mean, I've got right here in front of me some 2 micron diameter aluminium oxide particles mounted in epoxy resin, polished, ready to test. I can visualize them with the SPM nanopositioner, and I can then place the indents right in the particles. So,
okay, very good.
So yeah, they're small.
Okay, and that's actually he even asked follow up then. If we choose a crystal micron, a few microns crystal, sometimes it's not very smooth.
Mm-hmm.
Can we modify surface roughness?
Well, you can go through the polishing process. I mean, it's the case. The aluminium oxide particles I'm talking about are probably some of the easier ones to prepare, but there are materials which are less easy. I mean, polishing basically. Sometimes you might have to some materials polish dry. Okay, some materials reactive with water.
Polishing mounted in epoxy, is it essentially the best?
Yeah, it's mounted. They're using a hard epoxy, metallographic mounting epoxy.
Okay, so and how sharp? So I'll just jump on one question to Joan. How sharp can the Berkovich be purchased nowadays? Can we? What do we supply typically as our sharp? And now to define sharpness, I guess, for Berkovich as well. But what do we mean exactly?
I think realistically, 50 nanometers is still. I think people claim all sorts of things, but I think you can simply indent them and look at transition pressures essentially, and convince yourself actually that they're nowhere near as sharp as people think they are. But I think in practice we can be very, very confident of sort of a lot of our indenters can be around that sort of 50 nanometer mark.
Good.
So I think the claims of 20 nanometer indenters, I think, are possibly taken. That's more like an AFM probe geometry.
But I asked one manufacturer who actually claimed to make those. I said I'd like a couple of those, and they very quickly backpedaled from being able to offer them.
Okay, so let's get to our last question. Our last question is from Hubert. If we are getting scattered results, such as Ben showed, related to relative humidity, how can we then determine the actual material property in case of coatings with minimal roughness?
I think RH actually means not relative humidity.
RH, relative
hardness.
No,
I showed a slide where the material itself was very homogeneous, but the curves were scattered, and the reason why the curves were scattered is they were done at different moisture levels in the chamber. So
right.
So in this case, I guess the question is why, if you're getting scattered results and you've got a very, very smooth surface, then that's telling you that your coating itself is actually microstructurally heterogeneous, and you actually the variation in results is picking up due to different mechanical properties in different phases in the microstructure. If you've designed your experiment, that's what it's telling you. the materials that look homogeneous, like a steel or something, as you go down and down and down, then suddenly at some point the results split out as you start to become sensitive to the individual phases, not the bulk properties, which is the main reason for doing the technique, to get that local mechanical property information.
Yeah.
Okay. Very good. That's our last question. I'll close at that point. Thank you for those who stayed with us. If overrun, but I hope answering all the questions was interesting for you. We again remind you that you can pick up a certificate of attendance at the link we sent. It will also be on a follow-up. You'll get a follow-up email from us thanking you for joining the seminar. That link will be in there as well. Microtils is always happy to field questions from you. I've always mentioned our LinkedIn page is a good source of these events. If you do want that slide set, I put my a modified slide, subset of the slides we showed today. Then I've put my email up there because that will come from us rather than from the organisers of this seminar. I'll put it up once more if I can type correctly and type under pressure. Yeah, we'll get you a subset of this of the information of the slides that were shown today. So on that, thank you for joining, and thank you for Ben, thank you Andy earlier, and thank you for Adrian for your time that you made to present this. Yeah, we do this regularly, so yeah, keep an eye out, and we will start to take it from the basics to the more specialized options. And as I pointed out, high temperature one is next, even though it's very late in the working day for Europe. Okay, thank you very much, and thank you for your time today.
Okay, thank you. Bye everyone.
Bye.